So we continue now. So basically, this L2 is the maximum length of the plastic region that can grow in the material. Now, it has some very important significance. You remember in the case where we were discussing elastic deformation of the mortar, we said we will always have a very non-uniform stress distribution, shear stress distribution, and the two ends of the mortar were participating more, were carrying more load than the majority of the mortar. But if the plastic region is deformed, is expanding all along, that conclusion goes out of the window, because in the plastic deformation, we have elastic, perfectly plastic response. So the whole mortar can be experiencing the same stress, which is tau f. So in some sense, unlike the elastic region, all of the material now can participate to this load bearing. Now, but there's a big if here. For us to get this, we need to get to sufficiently high sigma zeros. What does sufficiently high mean? It means at the highest level of sigma zero at which this happens, the tablets should still be able to survive. In other words, the sigma zero that causes this plastic deformation in the mortar should be less than or equal to the strength of the bricks. So sigma is the strength of the bricks. And keep in mind, we have two of L2, one on each side. So then, in that case, that gives us another length, which is, so basically the equation becomes sigma f times p is the force carried by the mortar by the brick at the far right end, assuming that the tablet and mortar, assuming that when the brick is about to fail, the whole tablet, the whole mortar has deformed plastically. Let me say it again. When the brick is about to fail, where sigma zero is approaching sigma f, in which case the force in the tablet will be, or bricks will be this much. At that point, the whole mortar is reaching plastic deformations. So the force carried by the mortar is going to be this. This too comes from the symmetry in the plastic region. We have one in the left, one in the right. So now, but at the same time, if we want to, and that gives us another length 2L star, which is basically this divided by that. Now, if your brick is longer than this 2L star, 2L double star, the rest of it are the regions that have, the rest of it are regions on which the mortar has broken. So those are the useless parts of the tablet. So that gives us another critical dimension, just like L0 that we had in the elastic region, to maximize basically the elastic energy density. And so now the summary is that we have two critical lengths, the critical length of the tablet. One is this L star is basically the basically the length at which the elastic energy density, critical elastic energy density, the maximum elastic energy density that can store in the material will be maximized for a given material properties. So this just tells us if we have this ingredients in this biological material, what the L star should be for elastic energy density to be maximized. And we also had one more critical length, which is this guy that we calculated here. This is the one that allows us to most effectively use the mortar, and so that we ensure that all the mortar can, at the end of the deform, at the maximum load that you can carry, is now deforming plastically. So it enforces you to put maximum amounts of energy that you can put in this guy to break it. So let me stop here this video, and then I will go back with this to the slides that we had earlier.